Welcome back. In this lecture video, we move into the next module, which is on ratio and regression estimation. Now, these are not sampling techniques, these are estimation techniques, and they are techniques that can give our estimators greater precision. The first topic we'll look at is called ratio estimation. Suppose that two response variables, y and x, are available for measurement. Denote the population means of these variables by mu sub y and mu sub x respectively, so that mu sub y is the mean of y and mu sub x is the mean of x. In the present context, it will be assumed that the population means are proportional, that is, that there exists a non-zero constant k such that the ratio of the population means mu sub y over mu sub x is equal to this proportionality constant k, and therefore that mu sub y is equal to k times mu sub x. Now this would occur, for example, under a model of the following form: y equal to k times x plus epsilon. You may recognize this as a type of simple linear regression model where the intercept is equal to 0. And so this is a type of regression model that assumes a proportionality relationship between the expected value of y and the expected value of x. Now our interest will be in using this relationship between the means of the response variables as a basis for estimation of the unknown value of mu sub y when mu sub x is known, but the proportionality constant k is unknown. Now, if an estimator of k can be obtained, and we will denote such an estimator of k by k hat, then an estimator of mu sub y based on this proportionality relationship would be given by the following. Our estimate of mu sub y, mu hat sub y, is equal to k hat times mu sub x. So again, in order to utilize this kind of estimation procedure, we would have to know mu sub x, and then we would also have to estimate k. And if we can do that, then as long as this type of proportionality relationship holds, right, and again, that would hold under a special case simple linear regression model that I'm showing here on the bottom of slide 3, then as long as that's the case, then we can estimate the mean of y in this fashion. So our first task will be to find an estimator of the proportionality constant k. All right, so let's see how we can do this. And so we start off with a bivariate sample. So let the ordered pairs x1, y1, and x2, y2, and so forth up to x sub n, y sub n be a bivariate simple random sample of size n from a finite population of size n. Now notice that what we're looking at here in this particular context is a simple random sample, a bivariate simple random sample from this finite population of size n. Okay, then we'll let y bar be the mean of the y values and x bar be the mean of the x values. All right. Then a ratio estimator of the proportionality constant k is given by the ratio of the mean of the y values to the mean of the x values. And we can also express that as the ratio of the sum of the y values to the sum of the x values, because in both the numerator and the denominator we've got a 1 over n, and those 1 over n's cancel out. So this would be one way to come up with an estimator of k. Now note that while y bar and x bar individually are unbiased estimators of mu sub y and mu sub x respectively, and by the way, that should be fairly clear by this point because these are the means of sample data selected from a simple, or that are part of a simple random sample selected from the population. So note that while y bar and x bar individually are unbiased estimators of mu sub y and mu sub x respectively, in general, it is the case that the expected value of the ratio of those sample means is not equal to the ratio of the expected values of the sample means. And so what the implication of this is that k hat is not an unbiased estimator of the proportionality constant k. All right, so this is a situation where we will really have to make use of a estimator that is somewhat biased. Now, the other issue here is that the exact form of the variance of k hat is unknown and therefore will need to be approximated. So k hat is an estimator of k, but it's not an unbiased estimator. It's got some bias to it. All right, and the amount of bias is not known. And to top it off, we don't know the actual expression for the variance of k hat. Now, compare that or contrast that with the previous situations that we've looked at up to this point. In those situations, we've always been able to come up with the expression for the variance of our estimator in those situations where we needed it. Now, we couldn't calculate the values of the variance of an estimator if we didn't know the underlying population variances and so forth, and so we had to estimate it, but at least we had that expression that gave us the functional form for the variance of the estimator. But in this case, we don't even have that, right? And so we will need to approximate the variance of k hat. And so with this in view and incorporating this approximation, which we're not really going to go into, I'll give the expression here, but I'm not going to go into the theoretical development or derivation of that approximation. But we have it here. The estimated variance of the sampling distribution of k hat is given by this expression here. So we are going immediately here to the estimated variance. And in fact, I should really say it's the estimated approximate variance of the sampling distribution of k hat. And so we can see here that it involves the population size, cap n, the sample size, little n. It involves the x's and the y's. Notice also that this estimated approximate variance also depends on mu sub x, the mean of the population of x values. Now, again, in much of what we're doing in this module, many of these procedures are based on an assumption that we would at some point when we would go to use a technique like this, we would know what mu sub x is. All right, and so that's why we included here. This is the component that provides the approximate variance formula. Now notice also that this estimated approximate variance is not an unbiased estimator of the true variance of k hat. Now once we have this estimated approximate variance of k hat, then we can get the corresponding standard deviation of the sampling distribution of k hat by taking the square root of that quantity. All right, and again, this would be the estimator for the approximate standard deviation of k hat. Now, this expression, which is part of this estimated approximate variance, shows up here in the variance, and then it also shows up obviously down here in the estimated standard error. Okay, this expression shows up in many variation formulas in this particular section in this module, and it's quite tedious to compute in this form, all right, because we would have to evaluate k hat and then multiply k hat against x sub I, do that subtraction from the corresponding value of y sub I, and then square that difference and do it for every observation in the sample. So it becomes somewhat tedious and prone to error, and we want to minimize the chance of making calculation errors and so forth, and we want to cut down on the tedium. And so we have a shortcut formula which tends to be a little bit easier to use because you've only got to calculate the quantities on the right hand side of this equality and then put them together in this way. So we add up the squared y values, we add up the squared x values, we add up the products of the x's and y's, We calculate k hat from the data, and then we put them together in this form, and that is equivalent then to, it's equal to this quantity, the sum I going from 1 up to n of the square of y sub I minus k hat times x sub I. All right, so this is, again, an easier way to calculate that quantity, and then once we have it, we can plug that into the formula for the estimated variance and estimated standard deviation of the sampling distribution of k hat. Now, in some cases, we may want to construct confidence intervals for k hat, and so one way to do that would be to take this estimated standard error of k hat, multiply it by 2, all right, to come up with the estimated approximate 95% margin of error associated with k hat, and we could actually call this the estimated approximate 95% margin of error, because a 95% is an approximate coverage probability. Also, this is the estimated approximate standard error of k hat, and so we see that we've got lots of approximation going on here as well as estimation. Now, we're obviously not going to use that kind of terminology typically, but I do want you to be aware of the fact that we've got, two levels of approximation, or two aspects of approximation going on here in addition to the estimation from the data. Okay, so once we have the estimated approximate 95% margin of error associated with k hat, then we can calculate the approximate 95% confidence interval estimate of k by taking our point estimate of k, which is k hat, and then from k hat subtracting off the estimated approximate 95% margin of error to get the lower end point, and then adding to k hat that same quantity, that same margin of error to get the upper end point. All right, and so when we do that, then we obtain our approximate 95% confidence interval estimate for k. So again, in some situations, it may be of interest to come up with a confidence interval for this proportionality constant k, and if so, then this is how we could do it. All right, so let's look at an example. This would be example 1 in this module, estimating a proportionality constant k using a ratio estimator. All right, so in a survey to examine trends in real estate, an analyst is interested in the relative change over a 2-year period in the assessed values of homes in a particular community. A simple random sample of little n equal to 20 homes is selected from the population of capital N equal to 1,000 homes in the community from tax records, and the investigator obtains the assessed value for this year. All right, so the assessed value for a home will be denoted by Y, and the corresponding value 2 years ago, and so the assessed value 2 years ago will be denoted by X. And they've obtained this information, this bivariate data for each of the 20 homes included in the sample. The realtor or the investigator wishes to estimate K, the proportional change in the assessed value for all 1,000 homes in the population, but doing it using information contained only in the sample. All right, so here are the data. These are in units of $10,000, and this is obviously dated data. All right, but that's fine. We'll use it as an example. Now, because of the layout here on the slide and the limited real estate on the slide, we're not able to list the data using ordered pairs, or at least not conveniently, but they do line up in terms of position, right? And so the 6.7 goes along with 7.1, the 8.2 goes along with 7.4, and so forth, out to the last pair of values. The 8.9 goes along with the 9.4. So the corresponding X and Y values are paired. Now, using these data, we want to estimate K, the proportional change in real estate valuation over the 2-year period, compute the approximate margin of error associated with the estimate, and in addition, construct an approximate 95% confidence interval estimate of K. Okay, so we write down what we know here. We know that cap N is equal to 1,000, little n, the sample size, and this is a simple random sample from the population of 1,000 homes, but little n is equal to 20. And then we calculate the following summary statistics. The sum of the x's is 154.5. The sum of the y's is 164.7. The sum of the squared x values is 1210.55. And the sum of the squared y values is 1373.71. We also need the sum of the products of the x's and the y's, and that turns out to be 1288.95. So these are the summary statistics that we'll need in order to estimate k hat, calculate the margin of error, and then construct the confidence intervals. And so the first thing we want to do is calculate our estimate of k, which is k hat. There are two formulas that we can use to calculate k hat. One would be the ratio of the sample means, all right, which we don't have up here. All we have are the sums. But we can also express k hat in terms of the sums of the variables, which is what I've done here. All right, so k hat is equal to the ratio of the sum of the y values to the sum of the x values. It turns out to be 164.7 divided by 154.5, and that is equal to 1.06602. All right, and so that would tell us then that over the 2 years for the homes in our sample, their assessed prices went up 6.602%. All right, next we're going to want to estimate the margin of error associated with k hat, and in order to do that, we need to calculate this quantity here. So the sum, I goes from 1 up to 20, of the square of each y value minus the predicted y value, which is k hat times x of I. Now again, we don't want to have to do 20 subtractions here. This would require doing 20 multiplications to get the k hat times the x of I for each I. Then we would have to turn around and subtract each of those from y. So that would be 20 subtractions, right? And that's going to be a bit tedious, but we can re-express this in this equivalent way. The sum of the squared y values, the sum of the squared x values, and then we have the sum of the products of the x's times the y's. All right, you can see here we have to multiply the sum of the squared x values by the square of k hat, and we have to multiply the sum of the products of the x's times the y's by 2 times k hat. And then we just put these quantities together according to this formula. And so when we do that, and you can see the calculations here, we get a value of 1.28441. All right, so that is the value of this expression here, which is part of the formula for the variance, the estimated variance of k hat. Okay, so here is the formula, all right, reproduced here, written down. And we know all of these values except mu sub x. So this is a situation right off the bat where we actually don't know mu sub x. So what we're going to do is we're going to estimate it, right? If we don't know a parameter, all right, we're going to estimate the parameter from the data, and recall that an unbiased estimator of mu sub x is equal to the mean of the x's, or x bar. So we'll use the sample mean, x bar, the sample mean of the x values, let me be clear about that, x bar, in this formula. And so now we've got, let's see, before we had estimated approximate 95%, now we're going to have estimated. So you can see we've got lots of things going on here. Now, when we do that, when we plug in a 7.725 as an estimate of mu sub x, then this is what we get for the estimated variance of k hat, 5.55074 times 10 to the negative fifth. All right, so again, that is the estimated variance of k hat. We need the estimated standard error of k hat, and that's just given by the square root of this quantity here. And so when we take the square root of 5.55074 times 10 to the minus fifth, we get 0.00745 or 7.45 times 10 to the minus third. Okay, we multiply that by 2 to get the estimated approximate 95% margin of error associated with k hat. That is equal to 0.01490. And then once we have that, then we subtract that quantity from k hat. Recall that k hat was equal to 1.0513. I'm sorry, it was 1.06602. When we do the subtraction, we get 1.0513. So this is the lower confidence limit for k. And then we also add the 0.01490 to the 1.06602 to get the upper endpoint of the confidence interval. And so what we can say here at this point is based on the data, we are approximately 95% confident that the proportionality constant relating mu sub y to mu sub x is somewhere between 1.0513 and 1.0809. So that is how we can estimate a proportionality constant using both a point estimator, k hat, and a approximate 95% confidence interval for k. And once we have that, then we can move on and try to and use this to estimate the population mean of y using some information that we have about the distribution, in particular the mean of x. So we'll look at that in the next lecture video.